Hello and welcome back to Introduction to Genetics and Evolution. In the previous video, we talked about this association between recombination rate and pi overall. We suggested that one possible explanation for why there's this positive association between recombination rate and pi is because you have frequent selective sweeps across the genome. This reduces a lot of variation in regions of low recombination, making it so they have low pi, and reduces very little variation in regions of high recombination, making it so they can sustain a high pi. Now, background selection is an alternative explanation for this pattern, and this is a continuing heated debate within the field of evolutionary biology in terms of its role relative to the other one. Now, I already gave you the positive view of the world, this idea that beneficial mutations around the genome cause this association between recombination rate and pi, this spread of adaptive variants. This was pioneered by these two fellows, David Begun and Chip Acquadro. Chip Acquadro is at Cornell, David Begun's now at the University of California at Davis. Now again, their idea is that there's very frequent selective sweeps on the genome, and that's what causes this overall positive association. Now the question is, what if beneficial mutations are actually very rare? Not just somewhat rare, but very rare. Well, if that's true, then you won't actually see a very strong overall trend because you'll actually have a lot of low recombination regions that may still have very high pi, right? That if you're not having a selective sweep that's eliminating the neutral variation there, they might sustain a fairly high pi. Well, in response to this, an alternative hypothesis was posed by this fellow. This is Professor Brian Charlesworth at the University of Edinburgh in Scotland. He suggests that bad mutations are very common, which we know is true, of course. When a bad mutation happens, interestingly what it'll do is it'll doom that allele and essentially the areas nearby it to eventual death. That over some period of time, even if you have a bad variant, it may be slow to get removed from a population, but it ultimately will be removed from the population. We saw this with some of those allele A1 simulations of detrimental variants that we did earlier. Now, importantly, the size of the doomed window varies with recombination rate. Okay? The size of this doomed window is going to vary with recombination rate. This process is referred to as background selection. Now let me illustrate this for you. So let's imagine background selection in a region with low or no recombination. Now what we have depicted here is background selection in a region of low or no recombination. So we have several neutral sites here. These blue ones are neutral. Okay, so this is essentially what diversity doesn't matter. And we have here a set of bad mutations that have arisen in this population. We see that we have a lot of bad mutations. We're assuming that these are fairly frequent. So what's going to happen? Well, all these chromosomes, if there's no recombination, all these ones that have a bad mutation are doomed, that they will not persist in the population. Eventually they will go away. So the only ones that persist are these. These are the only ones that will contribute to long future generations. In that regard, you notice we've lost all variation at those blue sites. Now everybody's T and everybody's C because we got rid of so many different variants. This is what happens when you have a region of low or no recombination. What if you have high recombination? Now, in this case, I'm putting in something kind of like recombination hotspots here. That's what those vertical bars are. We have the same two variable sites that we had before with the same frequencies, and we have the same bad mutations. What happens now, we now just lose those segments that actually have the bad mutations. Now, these are not deletions. They're not like cut out of the chromosomes. It's just, and when you're looking at how much variation is lost from the population, those pieces would get lost. But the areas around it can persist because they can recombine away. So when you look at it now and you look at the two variable sites, you still retain quite a bit of variation. This is the important difference here, that a lot more variability is being retained because the bad mutations can be lost without dragging away so much of the rest of the chromosome. So what is the prediction of background selection? Well, background selection assumes, and it depends upon, having very high rates of bad mutation. We know that's true. What it predicts is that regions of high recombination, where you have hotspots that are close together or numerous hotspots, will preserve more variation, high pi. So we expect high recombination to have high pi, or low recombination to have low pi. That's exactly the same prediction as what we saw with selective sweeps and hitchhiking. So where are we? Well, this is kind of a big debate. We see this association between recombination rate and nucleotide variation as measured as pi. Now, it could be that's resulting from selective sweeps, that these new advantageous mutations are arising fairly frequently, and as they spread and fix, they're taking away most of this variation. And neutral theory says that this should be very rare, that the neutral theory does not deny that selective sweeps occur, but it suggests they should be very rare. In contrast, background selection suggests that there's bad mutations happening all the time, and getting rid of them is what drags away variation. Now, the neutral theory has no problem with this, and this also generates the same prediction. We don't actually know which of these is true. This comes back to that neutralist selectionist debate that I suggest. This is essentially the new iteration of that. And this is very much an area of active research today. There's definitely continued disagreement. Here's a picture from a 2007 study looking at Drosophila simulans. The green there depicts levels of recombination. The blue depicts levels of nucleotide diversity measured as pi. And again, you see a fairly high correlation that when nucleotide variation is high, when recombination rate is high, nucleotide variation is high. Now, Begun argues that's mostly from hitchhiking, and he's shown that many beneficial mutations have actually been identified. Charlesworth argues that we know of many more cases of bad mutation. So let me give you a couple of perspectives on this. I actually contacted these people to get their input directly. Now, the recommended textbook that we have for you, the Freeman and Heron book, says the current consensus is that hitchhiking is probably responsible for the most dramatic instances of reduced polymorphism in linked regions, while background selection causes the less extreme cases. This is kind of a balanced view. Now, Begun tends to think background selection is not very important at all. He says there's no convincing evidence that background selection is a significant factor in Drosophila genome evolution at all. This is from an email dated 28th of February. So that's one end of the spectrum. At the other end, Dr. Charlesworth was a little bit less diplomatic in his wording, but he refers to a particular paper saying that they make a reasonable case that the reduced variability on the Y chromosome and 4th chromosome, these are chromosomes that have no recombination within species, can be explained very thoroughly by background selection. Well, this is very much an area that's still unsettled. Here's somebody else who's kind of in the middle. Suggests this controversy surrounding the relative significance of strongly beneficial and deleterious mutations in evolution has stimulated research activities for almost a decade. Despite efforts from many theorists and empiricists, fundamental questions are still open. Basically, the answer is, we don't really know. But again, still very much an active area of research today. How much of this correlation between recombination rate and nucleotide diversity comes from adaptive variation spreading or from bad mutations being eliminated from the population? Well, you can think about that yourself. Thanks for your time. I hope you enjoyed this video.